Afternoon, everyone. Our group did a project on temperature mapping the self-sustainable miniature swarm of robots. My name is Sally, and alongside William, Robin and Nick, we are your electronic engineers, and with Fern, Ian and Ben are our mechanicals. Okay, to start with, what is swarm robotics? Swarm robotics is the concept of multiple small decentralised robots that can act together to accomplish tasks beyond the capability of a single robot. With doing this, complex behaviour can emerge from individual operations. This is typically inspired by organisms such as ants, bees, birds and fish. This requires kind of three key features of a swarm. To be flexible, means they can cope in a spectrum of environments. They've got to be scalable, they're going to work irrespective of the group size, and they've got to be robust, so even if an individual is lost for any reason, the swarm can still function. Existing swarms currently use a centralised or a manual charging system, such as a charging station. This can be classified as a resource confliction, which limits the robustness and reduces the functionality of the swarm. So by employing an energy harvesting system, we hope to increase the robot range and the operating environment. This leads to our project aims, our primary aim being to design and manufacture 6 low-energy, self-sustaining robots that can temperature map a 3x3 metre grid which is smooth and has no obstacles. This leads to 3 specific aims of to design and manufacture robots capable of harvesting energy from a solar source autonomously, have robots that can communicate and behave as a swarm, and finally robots that can map temperature of tiles. As you can see, this leads to our work breakdown. This diagram shows our individual elements. As you can see, we've got quite interlinked individual work packages. They're interlinked with each other and across all of the different areas of the project, and this highlights the need for a central project management that I took on. Our treasurer was Janet Darby, and code management was underdone by Robin. Alongside this, we have our Gantt chart. This was pretty essential to ensuring continuous project flow and the fact that individual deadlines and testing dates could be completed on time.
In terms of the testing environment, we used a 3x3 metre testing grid. This was made using recycled wood, and the inside was painted with white gloss to increase the accuracy of the distance detection. In terms of the final testing, we were able to use a code motion tracking software, which is primarily used for biomechanics tracking, but we were able to repurpose this for use in the tracking of the robots by putting mini sensors on the top of the robots. This was mainly to validate the swarm behaviour and the general movement of the swarm, so that we have quantifiable data to look back on and see whether the swarm is performing as expected. To validate the temperature map side of things, we're able to borrow a thermal camera from the fluids lab and to be able to compare that against the temperature map that was produced by the robot and processed in MATLAB. For the main actuation design, it was decided to go for a simple differential drive solution. As the testing area was just a smooth and flat area, there was no need to tackle any complex terrain, so this was deemed suitable. To make this, to use a differential drive solution, we used a Pololu motor driver as well as 2 DC geared motors, and to help for balance, we also used 1 ball caster on each side of the robot, so basically the robot didn't tip over. From experimental testing, the maximum speed of the robots was 0.63 meters per second, with an estimated efficiency of about 86%. In terms of mechanical design, fitting all of the components into one housing unit, the main aim of this was to keep it as small as possible, while also keeping using the space efficiently. The main constraint on this was the size of the PCB, so the whole robot couldn't be smaller than this PCB design, but also including all of the sensors, the motors and the solar panel. All of the components, such as the 3D printed components and the laser cutting stuff, was done in the Fab Lab, and multiple robots. It was a very iterative design process where we would make one, see how it formed, and then make any changes that we needed to on the design, and then rebuild this robot. And finally, we manufactured 3 robots with the final iteration being a Fig 6.
So the electronic design focused around the Wi-Fi 3.0 microcontroller, which we used to do all decision making for the robots, all processing calculation, as well as all communication between the robots. So this was integrated into a PCB with 3 kind of modules of different components. The first one is the sensory modules, which are the LiDAR, which we use for location sensing, and the gyroscope, used for the same thing, as well as the temperature sensor to detect temperature. The control modules, just a motor driver, and then the power modules, which was to go from a LiPo battery to step up a voltage to power the Wi-Fi, as well as to step up a voltage to power some of the components. In addition, a solar panel was used with the robot, and charging circuitry was required to go from the low voltage and low current of the solar panel to the LiPo battery. All of this design was done for low power in general and was aimed to be very modular. So if a different mapping was done in the future, perhaps not temperature, a different sensor could be added to facilitate this.
As can be seen from figure 8, we've got a really good clear discharging curve here from the output of the robot's charging circuitry. This was achieved by running our 2 DC motors under no load, and they discharged in about 3.5 hours, which gives us some kind of estimate of how long each individual member of the swarm could function before they need to recharge. This is an obviously detectable voltage drop from about 3.9 volts to 3.4. This can be exploited to therefore monitor the remaining charge in the battery. We did this by implementing a threshold voltage, which gives the robot a low power warning. The solar panel was also used as a luminosity sensor to increase the simplicity of the robot. This was read using Wi-Fi 3.0's analog digital converter. Early observations and literature regarding industrial solar panels used for commercial power generation show that these panels typically produce more power when the light source is perpendicular to the panel. We experimented with our chosen panel by tilting it towards the light source, and we found it to be 30% more efficient when it was exactly perpendicular to the source, rather than it was just horizontal. Therefore, it was deemed viable to produce a mechanism to pan and tilt the panel to an optimal position for energy harvesting. The design was in keeping with key aspects of swarm robotic design. It was simple, modular, and compact. We used an SG90 microservo to tilt the panel, and the robot rotated on its centre to pan it. Although rotating the robot on its centre draws much more power compared to just tilting it to a microservo, this was implemented to reduce the number of actuators required. This was only implemented onto 1 prototype.
Another power management option is charge sharing. A limitation applied to charge sharing was that charge sharing could not affect the LiPo battery or the individual that shared charge. This meant that charge was shared between 2 supercapacitors, which were electronically isolated from the LiPo battery using an NPN transistor switch. Physically, the charge was shared over metal contacts of the plastic plate casing, as you can see at the top, and this led to system losses of 9.5%.
So to enable both the mapping and the self-sustaining behavior, we had to create a communication and behavior system for the robots to follow. So the behavior system was inspired by how locusts act in nature. So essentially how a locust works is that it will move towards a plant that is of high growth value, or a plant that it can eat, consume this plant, and then move on to another one, which is how a swarm of locusts can consume an entire field of crops quite quickly. And essentially we tried to mimic this by having our entire testing grid split into smaller tiles, as you can kind of see in the right-hand image. And then within each tile, we had a virtual plant that would grow by like 1 growth stage every time step. So then each robot, when it makes a decision about which tile it wants to go to, will choose the tile with the highest growth value, go to that tile, and after it maps it, it will reduce that growth value to 0 before moving on to another tile. In addition, when a robot is choosing a tile, it looks at the luminosity of the tile, and it weights the luminosity proportional to its current battery level. So low-power robots will want to move towards tiles with a higher light source on, higher ones don't care so much. In addition, distance was taken into account, so shorter distances are preferable. This is to save power and increase speed of mapping. All of these were combined into an algorithm, which was then simulated in processing. So figure 13 shows the simulation, where the orange tiles are tiles where the growth value is quite high, and the green tiles are where the growth value is lower, where a robot has recently mapped the tiles. In addition, a collision system was implemented, so robots cannot choose to go into the same tile another robot is in, and they can never choose the same tile that they intend to go to, so their next step. To facilitate this behavior, we needed a communication system. And this was inspired by glowworms. So in nature, glowworms will communicate information between each other by creating a luminescent pigment in their body. And essentially, it's a very broadcast-oriented communication system. There's no interchange of data between them. There's only broadcast. So we mimic this by having a Bluetooth system in advertising mode, which is essentially just a message is broadcast, and if you're in range, you receive it. The three main messages that were sent were of intent, which is where a robot intends to go next, mapping, if a robot maps the tile, it communicates this, and then luminosity, what the luminosity of the tile that it mapped was. In addition to sending this luminosity in the range of the Bluetooth communication of one robot, we also had it so that every time a robot maps a tile, it communicates to the highest light source it has ever had knowledge of. And the purpose of this is that, so within a Bluetooth mesh network, a relay node will generally, it'll repeat a message that it has received. And by having all of these robots transmit the highest light source they've ever seen, it will basically propagate through the entire swarm. So every single robot will know where the highest light source is. And the purpose of this is that on a local scale, we want exploration and mapping of tiles. But on a global scale, we want exploitation of the light sources. So in something like a cave, we don't want the robots going near a glowing moss or a light beam. We'd rather have them go to the entrance of the cave and go into broad sunlight to charge. In addition, the communication system facilitated charge sharing. If a robot is not near a light source and can't get to one, it will make a cry for help, essentially, and another robot will move to help it and share charge, as Sally mentioned earlier.
A shared global coordinate system was essential for the robots to distribute the location of the light source and for the collaborative temperature mapping aspect. Positional awareness was achieved using 4 LiDAR distance sensors combined with the gyroscope orientation. To obtain its coordinate, the robot would have to stop and move to the nearest 90-degree increment, rotate on the spot to the nearest 90-degree increment, read the sensors and calculate the coordinate before moving on. That map was used to write the program that would take the coordinate temperature data and collect it to produce a coloured temperature image of the arena. The function used for this MATLAB program required that every point in the grid be filled in before it could produce a map. We didn't want the robots to have to do this because it would take too long, and we wanted to still produce a map even if they couldn't complete the experiment for some reason. So instead, a function was used that interpolated the obtained points by the robots so that it completed and estimated the rest of the map. This was deemed to be sufficient so long as the robots collected enough points within the arena themselves, and these points were spread over the entire arena as well. The wireless data transfer from the robots to MATLAB was achieved using the Wi-Fi interface on the microcontroller.
So now we move on to results and discussion from experimentation done in the arena with motion tracking and other systems. And first, looking at communications, of the messages mentioned before, messages of intent and mapping worked perfectly, but the luminosity communications were quite inconsistent. So for the first few tiles that each robot mapped, no other robot would receive luminosity communications for it. However, after a short period of time, after these mappings, this would work. And if you look in figure 14, there's a left and right image, which are both console logs from 2 separate robots in a test. In the top left of them, there are values of 776 and 554. And in the bottom right, values of 110, which essentially shows that 2 robots have been in 2 different areas of luminosity and communicated this between themselves. The right-hand image in figure 14 shows robot 1 moving to a light source, failing to communicate the luminosity there, but then moving to the center of the grid and succeeding in communicating the luminosity. The second robot then turns to move towards the center of the grid, where it thinks a high light source is that it can charge at. In terms of the behavior then, so for mapping coverage, we had between 52 and 80% coverage for the map. More than this was not realized just because hardware errors and software errors often stopped some members of the swarm from functioning, so we couldn't complete a full mapping. The speed of mapping was around 2.7 tiles per minute, and there were 12 to 16% duplicate mappings. So it generally shows that during mapping, exploration is occurring rather than duplicate mappings of tiles that have already been visited.
In terms of what was achieved for power management and energy harvesting, the solar energy harvesting was particularly effective. It charged the curve, figure 16 shows the charging curve. It managed to charge the LiPo battery to a nominal level in about 2.5 hours, which goes to prove the potential for the self-sustaining aspect. The paddle was also an effective luminosity sensor. We had no problems using it to find the best panning and tilting angles and identifying the light sources. The only problems we had with this part was problems in reading the remaining charge level as the charging circuitry output. The readings were really quite noisy here, which occasionally gave false low power warnings. We attempted to use a moving point average to remedy this, but there was not time to fully implement it.
So the main temperature mapping experiment was intended for 3 robots, but only 2 could complete it due to an undiagnosed software or hardware error. The coordinate system was consistently accurate to 3 centimetres, and that meant that the distribution of points collected for the temperature map was reliable. It was found that it was infeasible to assess the accuracy of the temperature map with the thermal camera image, and this was mainly due to the difference in temperature range picked up by the image and the map. So in the thermal camera image, the thermal camera picked up the heat of bulbs, which is about 50 degrees, and that meant that the total temperature variation in the image was about 30 degrees. Whereas in the map, the robot temperature sensors only noticed the variation of a few degrees. So that's why it was difficult to assess how accurate the map was. What we could judge from the map though, so in the experiment, the robots actually completed it without having mapped much of the lower right-hand corner of the grid, and that led to a false area of coolness in the bottom. And that highlighted the importance of complete arena coverage by the robots before this mapping program was used. We also completed a few other experiments proving the concept of some self-sustaining aspects of the swarm. First, the shared knowledge of a light source location meant that the robots, upon being on low charge, could go directly to a light source even if it had not been the one to find that light source in the first place. And in another experiment, a robot was sent out a distress call because it was on critically low charge. So it stayed still, broadcasted its coordinate, and the second robot in the grid received that and moved directly to that robot's side. And that would be where the charge sharing element would occur.
So far we've mentioned that the project was held back by some technical problems. So I thought we'd outline some of the key and most difficult ones we had to solve. The first major problem we had was when we were trying to use the motors with the sensors at the same time. So as soon as the motors were switched on, we get fatal errors produced on the 4 LiDAR sensors and our gyroscope. However, our temperature sensor and the ADC for the solar panel continue to function properly. We've seen these errors before when we had poor connections between the sensors and the microcontroller. This is the most technically challenging problem we faced, and it delayed our project by about 2.5 weeks. Through general testing, we noticed that a slightly different set of motors function perfectly. These geared DC motors are an open source design, so many different manufacturers produce slightly different products, but which seem identical. Using a better made set of motors worked perfectly. These ones turn more freely, so I concluded that they produce less electrical noise and therefore do not induce currents in the sensors and thus causing the fatal errors. This was also an easy problem to solve because we simply deployed these motors across the whole swarm. The second major issue was some unexpected gyro readings. This occurred when we were testing a single robot for the first time and mapping the entire grid. After about 5 minutes of successful mapping, the yaw readings from the gyro began to randomly jump, even when the robot itself was not actually rotating. This was caused by delays in the threaded gyroscope from the microcontroller being occupied by other processes. This caused something that caused the feed-in, feed-out flow on the gyro to overflow and the readings to jump. We identified this by running the gyroscope independently and introducing 4 loops into the code to simulate the microcontroller being occupied. After some research and testing, we found that resetting the FIFO code after every iteration solved the issue completely.
We could summarise the main tasks completed in the project in 6 main conclusions. Firstly, quite clearly, only 3 robots were manufactured instead of the original intended 6. It became apparent throughout the project, especially after time delays and increasing costs, that our time would be more productively spent proving the self-sustaining swarm behaviours with the robots we had, instead of continuing to manufacture more. 3 was the number we deemed minimum to prove these swarm-like behaviours. The glowworm and locust-inspired algorithms were very effective for collaborative temperature mapping, and the communication system meant that information could be shared between robots. Solar energy harvesting was successful with the LiPo battery and the implemented charging circuitry. Battery levels were monitored, which allowed for intelligent and automatic charge management. The coordinate system was consistently accurate and robust to 3 centimetres, and it worked really well in conjunction with PID movement. And finally, the temperature mapping with multiple robots was successful, but work is still required to validate the accuracy of the temperature map.
In terms of future work, there are quite a few things which we'd suggest for the next year's group. So firstly, in terms of the PID tuning, that was particularly difficult just because there were many factors that completely changed the characteristics of the PID system, such as the robot, the power board, the floor we were running on. So for the future, we'd recommend that the next group use encoders on the wheels to be able to track the position of the wheels a lot better and hopefully standardize this across the whole swarm. To use a continuous coordinate system, so as Bern mentioned earlier, we'd have to move for a short period of time, go to the nearest 90-degree increment to get the coordinate, whereas with a continuous coordinate system, we'd be able to get the coordinate at any angle. And also linked in with that with a single PID controller, because currently there's a rotational function and a linear movement function, both PID systems, whereas in the future with a continuous coordinate system, to be able to link that in with one PID controller based on equations of motion. Next, in terms of collision avoidance and collision detection, so currently that is based on the behaviour side of things, but in the future that hopefully be based on a more precise LiDAR. To be able to function in an unknown environment, so currently we're having to operate in a 3x3 metre grid, but eventually we'd hope to be able to throw the robots down in any sort of environment and they'd be able to work straight away. To be able to deploy the charge sharing element and the solar panel actuation across the whole swarm to increase energy harvesting. And we spent a significant amount of time testing and debugging and trying to get rid of issues. So we'd recommend for the future that debugging methods, or better debugging methods, were implemented and further testing conducted to improve the robustness of the swarm.
All of this led to our final spend of £650.21. If you consider only the elements and the materials we put into the robot, this is a robot cost of £103.62. Even though this seems quite high due to the small scale nature of the project and hopefully being able to mass buy components in the future, we think this is pretty reasonable. Health and safety, we aligned alongside literature and the university's health and safety procedures. Everyone had to do a lab induction for the mechanical or the electronic workshop where necessary, and contacted staff when they were uncertain about what to do. When training was not available, protocols and procedures sheet was developed. This abstract here shows specifically for lithium batteries to ensure safe and confident use around them. We'd like to thank our project supervisor, Divin Zhu, alongside other university staff members, including Pete Armitage, Roger Parrott, Russell Edge, Martin Gill, James Bassett, and Gary Massey. Thank you very much for listening. Have you got any questions?
Very nice talk. I've got one question regarding your control strategies. So for data processing, single collections, and the single processing or the optimization algorithms, have these been centralized on computers or they are being distributed across different swarm units?
They're all local each robots, so they will run on microcontroller locally.
What's the advantage of using that rather than using a centralized strategy or considering using a hybrid strategy?
Mainly durability, so it's distributed, so it doesn't rely on one centralized controller. So if the centralized controller goes down, that's your swarm running as well. So that's the whole point of the swarm robotics really, is to get rid of the centralized system, distribute it across all people and agents.
Thanks.
I'm just curious, what's the dimension size of the robot?
So the final dimension is probably about 15 centimeters by 10 centimeters by each one, sort of thing. So initially we thought they're going to be smaller, but sort of issues and sort of other components meant they had to be a bit bigger, but they weren't massive. They weren't big enough.
Mainly it came down to the PCB size, so we didn't have the manufacturing techniques to make ridiculously small PCBs or multi-layer PCBs, so it really came down to how big that was going to be. So, yeah.
Do you think in the future we can make it smaller?
Well, if one would outsource, let's say, PCB manufacturing, you could make a more complicated design and reduce the footprint and use smaller components, and there's a lot that could be done with better manufacturing techniques. But a lot of components we had to use were a lot larger than just so that we could hand assemble it. So, yeah.
Solar panels has quite big to actually charge our robot in a decent amount of time. So that's another thing.
You said the robots don't collide with each other because they don't do the same location. Is it a collide on the list?
So essentially, when they choose the location they're going to, they can only choose a cardinal direction. So they can only go northeast, southwest, a single tile, and they know the intent of all of the robots. So they can never choose to move in the same direction because they only move one tile at a time. They can't cross paths.
And the tiles are small, they're only 30 by 30 centimetres, so 60 by 60.
No more questions. Thanks very much.